Welcome to Computer Architecture. Today we're going to talk about floating point arithmetic in a 32-bit machine. Representing floating points we already discussed in the previous lecture, but now we're going to talk about doing arithmetic, doing addition of numbers in the right format in floating point in binary. So before we go to binary, let's look at two decimal numbers. And our decimal numbers are 500 and another number is 50,000. Now, just for the sake of clarity, we know that the sum of that is 50,500. And we can write that in scientific notation like this, 5.05 times 10 to the fourth. What is that scientific notation? Because we have exactly one digit to the left of the decimal point, and then since we moved the decimal point, because really the decimal point was on the right of this two zeros of the 50,500.0. So the point over there on the right of the 50,500, we have to move it over 1, 2, 3, 4 places till we get to the 5. And since we moved it over to the left 4 places, we have to multiply it times 10 to the fourth. And that will give it the same equivalent value. Now, I want to show you another way to do this math that seems less good, but it's actually more methodical. It follows a certain algorithm that we can reproduce in a computer better. So let's look at this. We have 500. Well, 500 is really 5 times 10 to the power of 2. Plus 50,000. 50,000 is 5 times 10 to the fourth. So what we can do is we can say like this. Let us equate the powers of the two numbers. So they're both 10 to the larger power, 10 to the fourth. So the 5 times 10 to the fourth we're not going to change, but the 5 times 10 to the second we're going to change to 5 times 10 to the fourth. If we change it to 5 times 10 to the fourth, we have to move the decimal point accordingly, which means to the left, to get the same value. 5 times 10 to the fourth, 0.05 times 10 to the fourth is also 500. So now that the numbers are in the same are multiplied by 10 to the same power, we can cut and paste the power over on the right, the 10 times 10 to the fourth, and then just add the two numbers. So we've got 5 plus 0.05. So we get 5.05 times 10 to the fourth. So now we put everything into scientific notation, and we equated the powers, and we added, and we got our result. And we kept it in scientific notation. So we can say that we raise the power of the smaller of the two numbers. So let's do another example now in binary. So if we have 11.1 times 2 to the fourth, right? In binary, we always multiply by 2 to 2 power. Plus 0.11 times 2 to the fifth. So we notice that to the fourth is the lower power in this case. So we need to put them both to the power of the fifth. So this becomes, in order to change this to 2 to the fifth, we have to move the decimal place to the left by 1 place. So it becomes 1.11 times 2 to the fifth. Now if we add those two numbers together, so again we have 11.1 times 2 to the fourth becomes 1.11 times 2 to the fifth. And this number we don't have to change. So here on the right, I did the math, and I show you that this is the 1.11 times 2 to the fifth, and the 0.11 times 2 to the fifth we don't have to change. So I put it there. We add them together. 1 plus 1 is 1, 0, so put the 0, carry the 1. 1 plus 1 plus 1 is 1, 1, so we put the 1, carry the 1. 1 plus 1 is 1, 0, so we write 1, 0, and we're done. So we got 0.10 times 2 to the fifth. And that is our result. And it's right because we follow the same pattern as we saw works for decimal numbers. Wait a second. Okay. Now let's do an example where we start with decimal numbers and we put them into binary and then we add them together. Now, if we had 1 1/4, 1.125 is 1 1/4, plus 0.75, which is 3/4, obviously the right answer should be 2. But so let's just keep that in the back of our heads when we look at this. Now let's convert 1.25 to binary. Now, how do we convert that to binary? So if we remember, I can show you another slide here where each digit in binary, as we go to the right, after the decimal point, assuming these are after the decimal point, is 2 to the negative 1, 2 to the negative 2, 2 to the negative 3. Well, what is 2 to the negative 1? It's actually a half. What is 2? Because it's actually like 1 over 2. And this is 1 over 2 squared, which is 1 over 4, which is a quarter. So this is a half, this is a quarter, and this, of course, is an eighth, and this is a 16th. So this number here is a 16th plus, I don't know what that is, 128th or something like that. Okay, but back to our case. If we want to represent 1 1/4, it's 1. Well, if it would be 1.1, it would be 1 1/2. So we need to go a quarter is we go 1.01. So that's over here, 1.01. And times 2 to the 0th. Well, 2 to the 0th is 1. So we're always going to multiply it by 2 to the something. And then that's our 1.25. What about our 75? Or 0.75? Well, 0.75 is a quarter and a half. So that's first 0.1 is a half, and another 1 is a quarter. So a half and a quarter is 3/4. Times also 2 to the 0th. Now we want to add these numbers together. Now we could just add them straight, but really we're going to follow a certain procedure where we first normalize the numbers. Normalizing means we have exactly 1 digit to the left of the decimal point. Exactly 1, not more. And the digit is always going to be a 1, not a 0. Because if it would be a 0, we could move it over more and put the 1 there. So it's always going to be a 1 point something. I mean, except, of course, for the number 0 itself. But that's a side point. Okay, so 1.1 is our answer, but that's normalized. But since we moved the decimal points 1 to the right from the original number, which was 0.11, we have to multiply it by 2 to the negative 1. So now we have 2 powers. We're going to add. We want to add 1.01 to the times 2 to the 0th plus 1.1 times 2 to the negative 1. We need to equate the powers by raising the power of the lower number to that of the higher. And since the higher, in this case, is 0, and we need to raise the negative 1 to 0. So in order to do that, we have to move the decimal point back to the left again. And this seems kind of bizarre because we just moved it, but we're just following a certain procedure. It's true that this normalization meant we moved it to the right, and now we're moving to the left. But that's what we're going to do, and it's going to work, even though it's a little bit, extra work here. So 0, so we get now 0 times 0.11 times 2 to the second. And now we have our number, even though it's not normalized anymore, but at least it's the equated power. So we take 2 numbers that are normalized. Then we equate the powers, which means we're going to have to move the decimal point around. And then we can observe the following rule, which we just saw before, which is that if you have 2 numbers, A and B, and you want to add them, and they are multiplied by the same 2 to the same x, where x is the same number, it's equivalent to A plus B times 2 to the x. That's what we saw in the previous slide. So I'm just going to, for the moment, ignore the 2 to the 0. Well, here I write it down, and I'm going to add these numbers. 0.11 plus 1.01. Well, 1 and 1 is 0, carry the 1. 1 and 1 again is 0, carry the 1. 1 and 1 is 1, 0, so I get 10.00. And that's times 2 to the 0th power. But it's not normalized because there's more than 1 digit to the left of the decimal point. So here's where I got that number. Just again, it's 0.11 times 2 to the 0th plus 1.01 times 2 to the 0th, and I add those 2 numbers. That's my A and my B, and I leave the power, and I get 10.00 in my case times 2 to the 0th. But if I normalize it, I move the decimal point to the left, and it becomes 1.0 times 2 to the 1. So how am I going to write that in a 32-bit floating point number in a MIPS architecture? So the way I'm going to do it is I'm going to remember that first I take this number 1.0 and I throw away the 1 because the 1 is assumed. There's always going to be a 1 to the left of the decimal point. Remember, because these are binary numbers, it's always going to be a 1. It'll never be a 2 or a 3. And it also will never be a 0. Unless it's the number 0. But I throw away that number. And now I just write all those zeros. I have to write 23 zeros here. And then remember, it's a 32-bit number. I have 8 bits for the power. The power in this case is 1. But we say that the power is biased, which means that whatever number I write here, I'm going to subtract 127 from it. So in order to get a 1 here, which is what I want, the way I represent a 1 is by writing 128. And then when I subtract 127, so I take the 1 that I want, add 127 to it, I get 128. When I subtract now 127 from it, I'll back to the 1 again. So I write 128 when I really mean 1, which is what I want. So I'm going to write all these zeros, and then this 128 is actually a 1. And then the 0 over here is the sign bit, which being 0 means that it's a positive number. In other words, if it would be a negative number, I'd write a 1 here, but since it's a positive number, I'm going to write a 0 here. Okay. So far, so good. And now let's see another add example. Let's say I want to add this large number, 111010110, and I want to add it to 11001. Well, first thing I got to do is write them in binary. Sorry, it's in binary. Write it in scientific notation. And that means I would write 1.111110101 times 2 to the 7th. Why 7? Because I moved the decimal point 7 points to the left. So that's 2 to the 7th. Then this one, I'm going to write also 1.1001. Since I moved the decimal point to the left 4 places, I'm going to write 2 to the 4th. So now I've got my nice number, 2 times 2 to the 7th, 2 to the 4th, but I need to equate the powers of the 2, so it becomes, I need to move the decimal, I need to change it to a 7. If I want to change it to a 7, I'm going to need to move the decimal place 3 to the left. So it becomes 0.0011001 times 2 to the 7th. Now I have two equivalent numbers, they're both to the times 2 to the 7th. I can put them one over the other and add them together. And I'm going to get 1, 1, and I'm going to get 1, 0, and that's my number. Now I need to normalize that result, which means I'm going to move the decimal point over by 1. Now remember, this was a whole number. This number was not the answer. This number was times 2 to the 7th. So I'm going to still have it times 2 to the 7th, but now I'm adding a 1 to it since I moved the decimal place. So I get 1.000011 times 2 to the 8th. And that's my answer. By the way, in the previous example, just to show you, this number is, in fact, 2. 1, 0 is 2. Now we need to talk about overflow, because remember, these numbers could be really, really nice, but I'm adding a 1 to it. It could be that the exponent gets to be too big. The exponent has to be in a range of plus 127 to minus 127. Why do we say that? Because remember, we talked about this in the previous lecture, that we use 0 for representing 0. And as if the exponent is 0, then that's 0. And if the exponent is 255, then that's infinity. So we sort of throw away two numbers for the purpose of infinity and 0. So in our 8 bits, instead of it being from minus 127 to, minus 128 to plus 127, it's going to be from plus 127 to minus 126. But if our exponent is a smaller fraction than negative 127, then 2 to the negative 127. That's a very small fraction. If it's a smaller fraction, but not yet 0, but a smaller fraction, then that's called an underflow. Right? And as the number is too tiny of a fraction to represent. If the number is, if the exponent is greater than, if it's times 2 to 128, or greater than 127, that means the number is too large to represent, and it's an overflow. And that's how we have to be aware of this overflow. In such a case, we're going to say that there's an error. We can't represent the number. Now, let's go over the algorithm thus far, as we've seen it now, for addition. So, well, first I'm going to make a note that this will work for subtraction. How will this work for subtraction? Let's say we want to do A minus B. So we're not going to talk about subtraction. We're just going to talk about addition. That's what we have an algorithm for addition. But we can say that A minus B is the same as A plus negative B. And you say, yeah, but the number is a positive B. So we can flip a number from positive to negative or negative to positive by a rule, which is that if you do B tag, which means you flip all the bits of the number and add 1 to it, then that's the 2's complement representation of the number as a negative number. So even though we have 1 minus some negative number, we can flip it to be a positive number. B, we can change it to be plus a negative number by every place that there's a 1, we put a 0, and every place there's a 0, put a 1, flipping all the bits, and then adding the number 1 to it. So let's just prove that that's, by the way, for example, it's just, if you forgot from your course in digital systems, let's just do an example. This is 2 minus 1. 2 minus 1 should be 1. So what do? We take our 2, we write our 2. But our minus 1, we're going to change to plus negative 1. How do we write negative 1? Well, we flip the bits, so it becomes 1, 0. That's our 1, 0. And then we add 1 to it. So it's 1, 0 plus 1. So we have these 3 numbers to add together now. 1, 0 plus 1, 0 plus our 1 plus our 0, 1. If we add them all together, we get 0, 0, and 1 is 1. And 1 and 1 and 0 is 1, 0. Now, since we had 2 digits in our number, we're going to chop off this third digit. It's like extraneous. It's not in our framework. So, in our format. So, it goes away, and we're left with 0, 1. Well, 0, 1 is 1. That's exactly what 2 minus 1 is. And you can say, well, that's not fair. You just chopped that away because you didn't want it. But actually, it's quite fair, because if we'd wanted 3, let's say it had been a 3-digit number, then instead of writing 1, 0, we would have written 0, 1, 0. And instead of flipping this bit from 0, 1, we would have flipped it, we would have started off at 0, 0, 1, and we would have gotten 1, 1, 0. So it would have been a completely different addition here, and it would have resulted in the same number. It would have been 1, 0, 0, 1. So it actually does work for whatever size. You have to decide how many digits you're representing, so that when you flip, you're flipping the right number of digits. And then you have to chop off. You can't add extra digits. So that works. That's how you do subtraction. So let's go back to our algorithm for addition. Given 2 floating point numbers, here's what we're going to do. First, we're going to equate the powers by increasing the power of the smaller number. We saw that. And moving the decimal point accordingly. So if we've raised the power or lowered the power, we've got to move. We're never going to lower. We're going to raise the power. We're going to have to move the decimal point. Then we're going to add the numbers and ignore the power. Then we're going to normalize the result that we got into 1 point digit, BBB is digit, binary digit, times 2 to our exponent. And that exponent we have to add the normalization. We have to take the exponent that we had before, plus add to it the whatever normalization exponent we got. Now, because we moved the digit in our normalizing, we may have to add or potentially subtract from our bias digit, from our exponent that we had before. That's what we did. Then we need to check for overflow or underflow, which means if the exponent is larger than a permitted value or less than less than negative 126. And if it is out of range, then we have to create some kind of a hardware exception to notify the machine that we don't have the right result. Then we need to truncate or round the mantissa to 23 bits. We're going to talk more about that. But we need to, in other words, we need to create a 23-bit mantissa. Here, if this is our number, well, let's go back to another example. If this is our number, our mantissa is 00011. That's not a 23. We need to add some more zeros to the right to make it be 23 digits. Then if we get a negative result, we actually have to switch it to be positive by the same formula and set the sign bit to be 1. Because remember, a 0 is a positive number and a 1 is a negative number. We're not using 2's complement to represent this negative numbers. We're putting a sign bit of 1 or 0. If there is a mathematical overflow, in other words, if I added 2 numbers and I got too big of a number, more than 23 digits, then the overflow bit will be the sign. In other words, and we can normalize the result and then just adjust the exponent. Okay. Now, as far as rounding, I said we would talk about that more. So let's talk about that more. If our number is too large, too many digits, we're going to need to round the mantissa. So there's 3 methods of rounding. We're going to just focus on this middle one, which is the one that MIPS actually uses, which is called rounding half away from 0. That's the name of it, as opposed to rounding towards 0. If the truncated fraction is greater than or equal to half the base, then increase the last remaining digit. It minimizes errors. Now, this rule could also be for decimal numbers, but it also introduces a bias away from 0. Let's do an example of a 3-digit mantissa in binary. So we have, let's say, this is our mantissa, which means it's the number after it's 1 point and then 1 point and then 1 0 0 1 0 0. So that will become 1 0 1 because why? We only have a 3-digit mantissa, so it should really be 1 0 0. But the following digit, the next digit, is a 1, which means that this is more than half the base. The base is, in other words, it's more than 2. Sorry, it's more than its base is 2, and this is half or more. Really, remember that, or let's think about it like this: that the 1 here means it's a half, right? If it would be the 1 after the next, it would be a quarter. So if it's a half, it's essentially like 100.5. Well, 0.5 is, we're going to round it up. So we add the 1 to this 0, and we get 101. Let's do another example. 101, 100. So this is the same as the previous example, except that this 1 is there instead of a 0. So we add the 1 to the 1, and we get 10, or 2. So this becomes 110, 110. Notice the 1 and the 1 add together and becomes 10, so it becomes 110. Let's do a third example. Let's say I have 101, and then not a 1 after it, but a 011. Now I have 11, but it's a 0. The first one is a 0, so I add 0 to the 1, and I don't change the 1, so it remains just 101. Okay, that's how we round. So essentially, if you want to say it in other words, what we're doing is we're looking at the digit 1 beyond the size of our mantissa and simply adding that digit to our mantissa. So let's talk now about, that was all for addition, right? Let's talk now about multiplication. In multiplication, we're going to write the number in the float format. And we're going to add the exponents, because remember, the exponents are all base 2, right? The exponents are whatever the number is, the exponent is 2 to the whatever. So it's like, for example, it could be 2 squared, some number times 2 squared, times some number times 2 to the 5th. Well, whenever you have exponents of the same base, you can simply add add the exponents. So 2 squared times 2 to the 5th is 2 to the 7th. 5 plus 2 is 7. And then you still need to multiply the mantissas. So we multiply the mantissas. Then we're going to normalize the result, which is moving the decimal place. If the normalization creates a new exponent, then we're going to have to add that to our 7, to whatever we got in step 2. Then we need to round the result if needed, which we just learned about how to do. And then we need to put the point in the right place. Okay, so let's do an example. Let's do 5 times negative 0.4375. Now this looks like a very ugly number, but actually in binary that's a very easy number to represent because, well, let's approach it. How are we going to approach it? We're going to say, well, it's definitely not we're going to convert this number into binary. It's definitely not 0.1 something. It's not 0.1 something. Because if it would be 0.1, the 0.1 would already be a half. And it's not a half. It's less than a half. So we can't put a 1 there. We got to put a 0. But then it's a quarter. It's more than a quarter. So let's add another 1. So it'll be 0.01. And we've got a quarter. We've got 25. So if we were to subtract 25 from 43, from 4375, so 25, 25 from 43 is 18. True. 43 and 25 minus 40 would be 15, but this is 3, so it's 18. So it's 18. Now we're going to remove from it an eighth. An eighth is, what's an eighth? A quarter is 25, 0.25. An eighth is 0.125, or about 0.12. So 0.12 is less than 0.18, so we can put another one there. And so forth, and so forth. So we're going to realize that the representation of this number is actually 0.0111. I should have written that here somewhere, but I did. That's going to be the representation of this number, 0.0111. And that's what I wrote. But that, I wrote it sort of over here because what I did, though, is I also normalized it. Because if it's 0.01, that's not normalized. I got to get a 1 on the left side of the digit, of the decimal. So, of the decimal point, or of the point. It's not really a decimal point. Here it's a binary point, actually. On the left side of the point, I've got to put a 1. So if it was 0.01, I had to move the number over twice. Because if I moved it once, it would have been 0.1. And then I move it again, it would be 1.1. So in order to get this number, 1.110, I had to move it 2 points. So I to the left, so I put 2 to the negative 1, negative 2. And I keep the negative sign. That's this number. And the 5, well, that's pretty easy. It's 101. But I again have to normalize it. So it's going to be 1.01, which is, since I moved the decimal point to the left, 2 to the left. Here I moved it so I have to raise it to the squared. As here I made the number essentially smaller, so I got to multiply by a bigger number. Here I made the number bigger, so I have to multiply by negative 2. I moved the decimal place to the left here. Here I moved the decimal place to the right. In this number I moved it to the right, so I put negative. Here I moved it to the left, so I put positive 2. I moved it again 2 places, just by coincidence. They're both 2. Now that's 5, and that's 0.4375. Now, the next thing I do is I look at the powers, and I say, well, this is 2, and this is negative 2. So I add them together. That's what we said. You add together. And actually, it turns out that 2 plus negative 2 is 0, so sort of the powers go away, or they become 0. Now, I have to do the multiplication of this number and this number. So I'm going to write it over here on the right. Here's our 5, 1, 0, 1, 0. Now, I don't write the exponent I already took care of, because that's taken care of over here. That's the 0. But so I'm just going to treat the numbers as they are with the decimal point as it is. And 1.110 that we got from our 0.4375. And I multiply them, and I do an interesting thing. Anytime I see a 0 over here on the right, I just multiply this whole row by 0, so I write 4 zeros. Now I shift left, and I take the 1, and I see it's a 1, so I just copy everything. 1, 0, 1, 0, and I put the 0 in because I shifted. And again a 1, so again I shift and copy, shift and copy. Actually, we can note that when I'm doing a multiplication by this in binary, it's actually a little bit simpler than decimal. Because what I do is I either shift and copy if it's a 1. Every time the bottom number, which I could call the multiplier, is a 1, I shift and copy. Every time it's a 0, I shift and don't copy. Essentially writing 4 zeros is like I didn't copy the number. I just put zeros there. 0 is not going to affect the sum. So essentially I do nothing. I just shift it. I shift it when it's a 0, and I shift and copy when it's a 1. And then I add up all the numbers, and I get this nice number here. Now remembering to keep the decimal point in the right place. Because remember, there was 6 numbers to the right of the decimal points. It's 3 digits here and 3 digits here, 6 digits total. So when I finally got my total result, I double check and make sure I have 6 digits to the right of the decimal point. And that's what I have here. That's how math works. So I have 10 or 10.00110. Now I look at that number, and here I wrote it over here. And here it is, the 10, but I need to normalize it. So that number was times 2 to the 0th, because that's what we got over here, the 0. But now, since we're going to normalize it by moving the digit 1 to the left, I raise the power from 0 by 1 to 1. Essentially, I got to take that power that I had over here before. If it was 7, then it's going to be 8 over here. Whatever I had here, I'm going to increase it by 1. Then I take the number and I round it. And how do I round it? You follow the procedure that I had before. Well, look at this number. This number, if it was just 3, imagine it's just 3 digits. So if it's just 3 digits, well, why is it just 3 digits? Well, because these numbers they started off with were 3 digits. But let's imagine it's in a chip that's 3 digits of mantissa. But either way, the rule in math is that if you have a 3-digit number times, 3 after the decimal place is 3 digits, then you keep it at 3 digits. So I'm going to round this number. Now it should really be just 1.000 because that's 3 digits. But I look at the next digit and it's a 1 and I add it to it. So it becomes 1.001 times 2 to the 1. 2 to the 1 I already have. Now I got to, so that's my number. My exponent is 1. My mantissa is 001. This 1 I throw away because we were always going to assume that there's a 1 there. And I put the sign on the number. Well, this number is a positive number times a negative number, so the sign is going to be negative. So that's a 1 in the bit. So if we go back to the format, what we're going to have is a 1 over here in this box, which is the sign bit. And over here, we want to put also to the power of 1, which is, since we're going to take away 127, we have to add our exponent to 127. Our exponent, just like in this example, our exponent is also 1. So it's going to be 128, which is represented like this. So it'll be 1, and then 1 followed by 7 zeros. And then what are we going to write in the mantissa? Well, we're going to write, it's a little bit funny because we rounded it to 3. But we're going to write, 001. Well, really, if it would really be 23, we would write 00011, 0, and then a whole lot of zeros. If it's a 23 digit mantissa. But if it would be a 3-digit mantissa, which is different from our example, then it would just be 001. Okay. Now, division is the same as multiplication, except in the following way. Same except that in step 2, we subtract the exponents. That's how you do division. If you have 2 to the 7th divided by 2 to the 5th, then you subtract 5 from 7. 5 from 7 instead of adding them. And in step 3, you perform division. So, again, over here, we're going to subtract. We're not going to add the exponent, we're going to subtract. And here we're going to do division of the mantissa, binary division. And every other step is the same. So now I've shown you how to do multiplication and division and addition. I explained about rounding and the general algorithm for addition. Okay, I look forward to seeing you in the next lecture.